Module 10, Chapter 7.8, Partial Fractions. Before we begin to decompose rational expressions, we need to review a couple of basic concepts you might have forgotten. What is a rational expression? How do you reduce a rational expression? What is the domain of a rational expression? How do you add rational expressions, and how do you divide polynomials? Well, a rational expression is a quotient of two polynomials p and q, with q is not equal to 0. That is, it's a fraction of two algebraic expressions as long as the denominator is not 0. A rational expression is in lowest terms when the greatest common factor of its numerator and its denominator is 1. Some examples of rational expressions are listed: x minus 5 over x plus 3, x squared plus 4x minus 5 over x squared minus 1, and x squared plus x minus 5 over x squared minus 4x plus 3. Now, which of these rational expressions are in lowest terms? Well, x minus 5 over x plus 3, neither of those will factor, and so the GCF is 1. Now the second one, x squared plus 4x minus 5, if we look at factored form, that would be x and x plus 5 minus 1. And then down in the denominator we get x minus 1 times x plus 1. Notice we have a factor of x minus 1 available in the numerator and the denominator. So we say reduced form would be x plus 5 over x plus 1. Now the third one, the x squared plus x minus 5 will not factor. The denominator will, x minus 3, x minus 1, but because there's no common factors in the numerator and the denominator, then we say it's in lowest terms. Now the domain of the rational expression is the set of real numbers for which the expression is defined. That is, it's the set of numbers that do not give a 0 in the denominator. To find the domain, set the denominator equal to 0 and solve. The solution to this equation is not included in the domain of the rational expression. Okay, let's consider the first three we did. The domain of this one, well, if the denominator is equal to 0, if x plus 3 is equal to 0, that means x had to be negative 3. So the domain is all real numbers except negative 3. Or you can say x not equal to negative 3. Now the second one, we said we'll factor x plus 5 times x minus 1 over x minus 1, x plus 1. Now remember, we said that would reduce, but when we're talking about domain, we always look at the original function. What would make the denominator equal to 0? Well, if x minus 1 times x plus 1 is 0, which means x minus 1 is 0 or x plus 1 is 0, or x is 1 or x is negative 1. So the domain would be all x's except 1 and negative 1. Now the third one, we said the numerator would not factor, but when we're talking about domain, we don't care what's in the numerator. We are only concerned with denominator. So what would make the denominator equal to 0? Well, when x minus 3 or x minus 1 equals 0, so x minus 3 equals 0, x minus 1 equals 0, x equals 3, or x equals 1. So domain would be all numbers except 3 or 1. Now from now on, when writing rational expressions in lowest terms, we will assume these restrictions on the domain and we won't list them every single time. Now, to add like fractions or rational expressions, you add the numerators and keep the denominators. That is, a over c plus b over c would equal a plus b over c. For an example, add the following. We have a like fraction, so we add the numerators, 3x plus 2. We keep the denominator of y. Last review. To divide polynomials, use long division. If there is a remainder, you put it over the divisor and add it to the quotient. Now remember, we did synthetic division, but synthetic division only works when you're dividing by a linear binomial of the form x minus k. On ours, we're not. We're dividing by x squared plus 3. So we're going to set it up, x squared plus 3 divided into x to the 4th minus 3x to the 3rd plus x squared plus 5x. I'm going to go ahead and fill in all these missing powers to help keep the columns lined up. We divide first terms. X to the 4th divided by x to the 2nd, which is x to the 2nd. So I'm going to put that x to the 2nd over the x to the 2nd. Now when we multiply, x to the 2nd times 3 is 3x squared. We need to make sure that we bring it right under the other squared. And then x to the 2nd times x to the 2nd is x to the 4th. And we need to make sure that that goes under the x to the 4th. Now we subtract the polynomials by changing the signs. That goes to a negative, that goes to a negative. So we get 1x squared minus 3x squared, which is negative 2x squared. The negative 3x squared comes down, and the x to the 4th cancel, which is what they're supposed to do. Now we're going to bring down the next piece. Now we're going to divide first terms again. We've got negative 3x squared divided by x squared, which would give us negative 3x to the 3rd. That comes down, and that would cancel out, which is what it's supposed to do. Now we're ready to divide first terms again. Negative 3x to the 3rd divided by x to the 2nd, which would be negative 3x. So we're going to bring that over the negative 3x. Then we're going to multiply. Negative 3x times 3 would be negative 9x, keeping our x's lined up. Negative 3x times x squared would be negative 3x to the 3rd. Now subtract, which means we're going to change the signs. So we've got 5x and 9x, which is 14x. The negative 2x squared comes down. The negative 3x and positive 3x to the 3rd, those cancel, which is what's supposed to happen. And then we can bring down the 0. Now we need to divide one more time. Divide first term. Negative 2x squared divided by x squared, which is negative 2. Multiply. Negative 2 times 3 would be negative 6. Negative 2 times x squared would be negative 2x squared. Change the sign, so that goes to a plus, that goes to a plus. So we get 6 plus 14x. So our remainder is 14x plus 6. So we always take our remainder and put that back over the divisor. Now, the process of expressing a rational expression as the sum of two or more rational expressions is called decomposing a rational expression. The sum of the rational expressions is called the partial fraction decomposition. Each term in the sum is a partial fraction. In calculus, partial fraction decomposition provides a powerful technique for determining the integrals of rational functions. Now, there are several things to consider when finding the partial fraction decomposition of f of x over g of x. The first thing is we need proper fraction form. Okay, if f of x over g of x You can't see that real well, but if f of x over g of x is not a proper fraction, that is, a fraction in which the degree of the numerator is greater than or equal to the degree of the denominator, then we need to make it proper by dividing f of x by g of x using long division. Then apply the following steps to the remainder, which is now a proper fraction. Now remember, proper fraction, the degree of the numerator is less than the degree of the denominator. If f of x over g of x is a proper fraction, then we're going to apply the following steps. This is sort of a two-part step. Factor the denominator completely. You should have either factors of the form ax plus b to the m, which are linear factors, or cx squared plus dx plus e to the n, which are quadratic factors. If you have linear factors, then for each distinct linear factor, ax plus b, the decomposition must include the term a over ax plus b. For each repeated linear factor, the decomposition must include the terms a over ax plus b plus a2 over ax plus b squared, all the way up, one for each power of ax plus b to the m. For each distinct quadratic factor, cx squared plus dx plus e, the decomposition must include the term bx plus c, which means we've got a linear factor over cx squared plus dx plus e. For each repeated quadratic factor, cx squared plus dx plus e to the n, the decomposition must include the terms bx plus c for each power of that quadratic factor. Third, use algebraic techniques to solve for the constants in the numerators of the decomposition. We're going to do that by setting the original rational expression equal to the decomposition containing the constants. We're going to multiply both sides of the equation by the LCD, which is basically the factor of the original denominator. Then we're going to substitute values into the equation for x. Begin with choosing values not included in the domain if you can. Otherwise, choose some easy values like 0, 1, or -1 if that's possible. This should give you the values of the constants, or maybe a system of equations that can be solved. Okay, are you ready to try one? Find the partial fraction decomposition. Well, we've already got it factored. So, we have two types of factors. We have x and we have x plus 1. So we're going to say a over x plus b over x plus 1. You notice we list each factor. And then what we're going to do is we're going to multiply both sides of the equation by the LCD, which is x times x plus 1. Then we're going to do this side by x times x plus 1. Well, this first side, what happens is the denominator and the new piece cancels, so we get 3x plus 1. On the second side, the first term, the x's cancel, so we get a times x plus 1. On the third piece, when we multiply it by x, x plus 1, we get bx. So we get 3x plus 1 equals ax plus a plus bx. Now this is where we go through and we're trying to find what a and b are. So what we try is the original problem is undefined when x is equal to 0 or -1. So the first thing we're going to do is we're going to plug in 0. So we get 3 times 0 plus 1 equals a times 0 plus a plus b times 0. So we get 1 is equal to 0 plus a plus 0, which means a is equal to 1. Okay, now we're going to pick another value. Let's choose x as -1. So if we pick -1, that would give us 3 times -1 plus 1 equals a times -1 plus a plus b times -1. So we get -3 plus 1, which is -2, equals -1a plus a minus b. Now remember earlier we just said a was 1. So that means -2 equals -1 times 1 plus 1 minus b. -2 is equal to -1 plus 1 minus b. So -2 is equal to -b, which means b is equal to 2. So now we go back to our original decomposition, and now we know the values of a and b. So we get 1 over x plus 2 over x plus 1. And that is what we call the partial fraction decomposition. Okay, did that make sense? Let's try another one. Now this one's not in factored form, but let's start out. We should have asked this on the other one. Is this a proper fraction? Yes, we've got an x over x squared. So first thing we're going to do is factor the denominator, which would give us x plus 5 over, x times x minus 1. So we've got two linear factors. So we're going to set that up as a over x plus 5 plus b over x minus 1. Now we're going to set that back equal to the original function. LCD is x plus 5 times x minus 1. So we're going to multiply both sides of the equation by x plus 5 times x minus 1. This piece, x plus 5 times x minus 1. And this piece, when we distribute it to that whole side, would be x plus 5 times x minus 1. First side, everything cancels and we get x. Second side, x plus 5 cancels, so we get a times x minus 1. B's cancel, or the second term, x minus 1's cancel, so we get b times x plus 5. Now, instead of multiplying this one out, I'm just going to leave it in this form and do our substitutions here. Now, this original problem is going to be undefined when x is equal to, because it's x plus 5 equals 0, that means it's undefined at -5. X minus 1 equals 0 means it's undefined when x is 1. So I'm just going to plug in here. Let x be 1. Maybe it'll be a little bit easier. 1 equals a times 1 minus 1 plus b times 1 plus 5. So 1 equals a times 0 plus b times 6. So 1 equals 0 plus 6b. So b is equal to 1/6. Now, if b is 1/6, we still need to find a. So let's do our other plug. Let x be -5. So we'd get -5 equals a times x minus 1, but x is now -5. -5 minus 1 plus b times -5 plus 5. So we get -5 equals -6a plus 0b. So a would be, if we divide both sides by -6, a would be 5/6. So when we go back to plug it in our rational expression, a would be 5/6, so that's 5 over, I'm just going to call it 6 over x plus 5, rather than 5/6 over that, plus b is 1/6, and we'll call that 1/6 times x minus 1. So this would be how we would decompose the rational expression x over x squared plus 4x minus 5. Let's try another one. Okay, this time we've still got linear factors, but we have multiple factors. So what we're going to do is we're still going to start it out the same way. A over x plus 1 plus b over x plus 2 plus c over x plus 2 squared. Now remember, if we have a power on a factor, we've got to include every one of those powers. So when we go through and multiply both sides by the LCD, which is x plus 1, x plus 2 squared, then we distribute it on this side. It's x plus 1 times x plus 2 squared for every piece. X plus 1, x plus 2 squared, x plus 1, x plus 2 squared. Okay, first side, denominator cancels up here and we're only left with 2x. Second piece, we're left with a times x plus 2 squared. Next piece, one of the x plus 2's cancel, so we're left with b times x plus 1, x plus 2. And then the third piece, the x plus 2 squareds cancel, so we get c times x plus 1. I think it was a little bit easier going and plugging it in those factored forms, so I'm just going to leave it. Now remember, we can pick anything, but it's easier to pick things that would make the expression undefined. So x plus 1 equals 0 means x is negative 1. X plus 2 squared equals 0 means x is negative 2. So the first thing we're going to do is plug in negative 1. So we'd get 2 times negative 1 equals a times negative 1 plus 2 squared plus b times negative 1 plus 1 times negative 1 plus 2 plus c times negative 1 plus 1. Okay, everywhere we had an x, we plugged in negative 1. So we get negative 2 equals, now negative 1 plus 2 is 1. 1 squared is 1, so that's just a. Negative 1 plus 1 is 0. 0 times anything, that one's 0. And then the third one, c times negative 1 plus 1, that's also c times 0, which is also 0. So that says that a is negative 2. Now let's plug something else. Let's plug negative 2. So we get 2 times negative 2 equals a times negative 2 plus 2 squared plus b times negative 2 plus 1 times negative 2 plus 2 plus c times negative 2 plus 1. So we get negative 4 equals, well, negative 2 plus 2 is 0. 0 squared is 0 times a, so that one's still 0. Over here, negative 2 plus 1 is negative 1. Negative 2 plus 2 is 0, so b times negative 1 times 0 is still 0. C, we've got negative 2 plus 1 is negative 1. C times negative 1 would be negative c. So we've got negative 4 is equal to negative c, which says that c is equal to 4. Now, we're still not through. We don't have a b. We're out of undefined points. Let's just plug. Well, 0 is going to be pretty easy to plug. So if we plug 0, we get 2 times 0 equals a times 0 plus 2 squared plus b times 0 plus 1 times 0 plus 2 plus c times 0 plus 1. So what we get is 0 equals 0 plus 2 is 2. 2 squared is 4, so that would be 4a. 0 plus 1 is 1. 0 plus 2 is 2. 1 times 2 is 2 times b, that's going to be 2b. 0 plus 1 is 1. 1 times c is c. Now we know an a and a c, so we get 0 equals 4 times negative 2 plus 2b plus c is 4. I ran out of room, haven't I? So that says 0 equals negative 8 plus 2b plus 4. Working up. 0 equals negative 8 plus 4 is negative 4 plus 2b. Adding 4 equals 2b, which means b is equal to 2. So now we go all the way back up to our original problem, and we say that our partial fraction decomposition is negative 2 over x plus 1 plus, well, we said b was 2, 2 over x plus 2, and c would be 4 over x plus 2 squared, and that would be our decomposition. Sorry about all the lack of space. Okay, finally we've got one that's not an improper fraction. That's not a proper fraction. Okay, finally we have one that's not a proper fraction. The power in the numerator is greater than the power in the denominator. So the first thing we're going to do is divide. So we've got 3x squared plus 2x minus 1 into 6x to the 5th plus 7x to the 4th. Let's go ahead and fill in our missing powers. Plus 0x to the 3rd minus x squared plus 2x plus 0. Divide first term, so we've got 6x to the 5th divided by 3x to the 2nd, which is 2x to the 3rd. So I'm going to bring that over the 3rd. 2x to the 3rd. Now when we multiply around, 2x to the 3rd times negative 1 is negative 2x to the 3rd. 2x to the 3rd times 2x would be plus 4x to the 3rd. 2x to the 3rd times 3x squared would be 6x to the 5th. Subtract, which means we're going to change the signs. And as I change them, I just circle them to know I've changed them. So we get a 2x to the 3rd, 7x minus 4x. Whoops, that should have been a 4, shouldn't it? 7x to the 4th minus 4x to the 4th would be 3x to the 4th. And then 6x to the 5th minus 6x to the 5th, those cancel. So now we bring down our next term. Divide first terms again. 3x to the 4th divided by 3x to the 2nd, which is x squared. So we're going to bring up an x squared. Now we're going to multiply. X squared times negative 1 is negative x squared. X squared times 2x would be plus 2x to the 3rd. X squared times 3x squared would be 3x to the 4th. Subtract, that goes to a minus, that goes to a minus, that goes to a plus. Now in this case, those cancel, and those cancel, but we've still got this 2x out here. So what that means is we've got a remainder of 2x over 3x squared plus 2x minus 1. The first two terms of our quotient stays in our partial fraction decomposition. We are only concerned now with the remainder. So we're going to rewrite that as 2x over, now if we factor that, we've got 3x and x. We've got 1 and 1, 3x and 1x. We need a positive 3x and a negative 1 to give us a positive 2x. We've got linear factors. So we're going to say a over 3x minus 1 plus b over x plus 1. Multiplying both sides by LCD. LCD is 3x minus 1 times x plus 1. everything on the left side would cancel, so we get 2x. The first side, the first term, when we do 3x minus 1 and x plus 1, the 3x minus 1's cancel, so we get a times x plus 1. The second one, when we cancel the x plus 1's, we get b times 3x minus 1. Okay, what numbers do we want to plug? Well, this thing is undefined if 3x minus 1 equals 0, which means x is 1/3, or x plus 1 is 0, which means x is negative 1. Let's do x is negative 1 first. So we get 2 times negative 1, which is negative 2. We get equals a times negative 1 plus 1 is 0, plus b times 3 times negative 1 is negative 3, minus 1 is negative 4. So we get negative 2 equals negative 4b. Divide both sides by negative 4, and we get b is 1/2. Okay, now let's do it for a. Well, let's go through and let's let x be 1/3. So we've got 2 times 1/3 is equal to a times 1 plus 1/3 would be 1 1/3, which would be 4/3, plus b times 3 times 1/3 is 1 minus 1, so that one's just basically 0. So we get 2/3 is equal to 4/3 a. Multiply both sides by 3/4, and we get a is equal to 2/4, which is 1/2 also. So now when we go back up to our final answer, we've got 2x to the third plus x squared plus, now we've got 1/2 for a, so that would be 1/2 times 3x minus 1. And then we've also got 1/2 for b, which would be 1 on the top, 2 on the bottom, x plus 1. So this would be our partial fraction decomposition. Okay, you are now ready to complete this section of homework on MyMathLab. Once you have taken notes and successfully completed the homework sets, you are ready to take the Module 10 quiz. Now, after you've passed Module 10 quiz, and if your attendance grade is above a 70, you will need to take the final exam. Now remember, you must make at least a 70 on every quiz and the final exam in order to pass the course. When you finish the course, please let your instructor know to make sure there's nothing else you've got left to do.